Hi, today I'm going to go over a board that first was not turning on and it also had issues with backlight. It's an 820-2879 board for the 2010 A1278 machine. This is not going to be a real-time video. I didn't notice that the microscope camera was not actually plugged in while I was doing it, and I fucked up a few things along the way. I don't mind if you see me fuck up a little bit, but when I'm staring at something for an hour just trying to do the same thing over and over again, and you can't even see what it is I did because there's no microscope camera, there was really just no point in posting that one. So I'm going to go over the process for this. Now, when this board came in, it looked like this. So yeah, the first thing that I did was just rip that LVDS connector off the board completely because that's just that's fucked up and crappy, and that's just bad. I'm not going to say what the name of the guy. He is a good friend of mine. We get along well. When I went to CTIA, he actually drove me, from the airport. He's a good dude, which is precisely why I'm not going to tell the internet what his name is and attach, that LVDS to it. But yeah, he sends a decent amount of boards to me, and I do fix them. And well, let's start off with the first issue here. The first issue here is that when I plug it in, is that I don't get anything on the charger. I didn't get a green light on the charger. So let's go over that first. So, alright. Now in the last video I did go over some of the things you should check if you're not getting anything on the charger. And I am going to go over what I was looking for on this board and what was happening with it. Now, as I said, there's something called the one-wire circuit. And again, if you don't know why your adapter's not working, one of the first things I would suggest you do is look at the part of the schematic dedicated to the adapter. So, yeah, again, makes life easy when you think a little bit. So here is the adapter. Here's the actual MagSafe. So we have adapter sense. Now, where does adapter sense go? Adapter sense goes to this shit right here, which creates something called sys one wire, and it's attached to this other chip right here, U6901, which is powered by the 3.42 volt bus of the board. It has an input signal called SMC BC ACOC, and then it shoots out a signal over here called SMC BC ACOC VCC, which then causes this thing to shoot out something called sys one wire. It's a fairly simple circuit. Again, if you're not really sure what's going on, you have this thing, this shoots out, you have SMC BC ACOC, and you have 3.42 volts. So what my very, very small brain gets out of this whole thing is that this receives a signal. When it receives this signal, it then passes on a voltage, and it uses the power from 3.42 volt bus to create that. And when this here senses the adapter and senses this signal, it sends out something called sys one wire. So one of the things you should do, again, if you don't know how this circuit works, that's totally cool. You don't have to be expected to know everything. What you could do is simply take a working board and measure along on the working board and see what you're supposed to get. Again, I don't know what the fucking ACOC is. I didn't know years ago what an ACOC was. I didn't know yesterday what an ACOC is, and I sure as shit don't know today what an ACOC is. I don't. I have no idea what those four letters mean. Not a clue. And do I care? No, because I don't need to fix the fucking problem. So, well, what I did, now what happens often with this circuit is, very, very often, is that 3.42 volts is not present here. And by the way, again, if you don't know what PP3V42 is, you can simply measure it. And when you see that it's 3.42 volts, you'll get the idea that PP and the V and all that other crap, it's just filler, and that, just imagine the V as a decimal point and the V being at the end. 3.42 volts. So, if you measure over here, very often you'll find that you don't actually have 3.42 volts. So U6901 is, let me just, so now U6901 is this little thingy over here. Let's make sure, it's right here. And you can see that actually, even though this one did have 3.42 volts, you can see the probe point for it is really messed up. You see this crap? I'm just going to move this around because I don't know what the viewable range of the microscope camera is. This was good. I got it. And now, other thing I checked for was that SMC BC ACOC was actually being generated. I wanted to make sure that this was coming in here. So where does SMC BC ACOC come from? Gee, I don't know. Let's look. Let's do Control F. Again, you don't have to be a genius. You just have to know how to use Control F. Control F is awesome, man. It does cool things. It lets you like look through and actually find stuff. Here we go. So SMC underscore BC ACOG. So over here, it says charger signal, charger underscore ACOG equals SMC BC ACOG. So let's find charger ACOG and see where that goes. Let's continue going further down the rabbit hole. Okay, so as I go further down the rabbit hole, I see that that is a signal that is created by U7000. Now how do I know that the signal is created by here and not by the other components? Well, right over here it says charger ACOG and then it says out, which means that it's being generated by this and going out to other places. So that's how I know that this is an input signal on U6901, because it's coming out from here. It says out. Now there's two ways that this is generated. Firstly, you have to have charger DC in present. So charger DC in. That's, again, this sounds confusing, but here, from adapter, so that's power from the adapter. It goes through this diode here, this little resistor, and then after that you just have DC in present there. That's pretty much that. Then you have charger AC in, which is a little bit more complicated. So from the charger, you have this voltage divider created by R7010 and R7011. This voltage divider takes the 16 or 18 or 20 volts from the charger. The voltage of your charger will depend on whether your charger is a knockoff. And it makes it into 4 volts over here. So you have a resistor going between the 18 volts of the charger and charger AC in, and a resistor going between charger AC in and ground. Now, let's go back to U6901. Alright, so back over here. I measured over here, and I had SMC BC ACOG, right? So that signal is being created. So I did not have to troubleshoot the charger AC in, the charger DC in. I can just assume right now that my U7000 is fine. U7000 is that IC that creates that signal that I just showed you. That also is responsible for creating the 12 volt system power that everything runs off of. So most of the things in this board are created off of that 12 volt line. So that chip I'm pretty sure is fine. It's creating the signal I need, and it's even creating 12 volts. Next, I check over here, and I have 3.42 volts at the chip. By the way, if you don't have 3.42 volts at the chip, because that's a very common fault, let me show you that there right over here. So this chip over here needs 3.42 volts in this pin. This other thing right over here, again, I don't even know what this thing is for, I don't remember, I don't care, has 3.42 volts over there. So you can just run one wire from here to here, and you fix the circuit. And 90% of the time that's the problem, which is why Apple engineers call that the one-wire circuit. I'm confident that all the engineers at Apple call that the one-wire circuit because you can always fix it with one wire. Anyway, so I have SMC BC ACOG, I measured that, it was good. I have PP3V4 too, that was good. But on output, on pin 4 over here, I was not getting this SMC BC ACOG VCC. I was not getting that. Again, do I know what adding VCC to it means? I have no fucking clue, but I don't care. On a working board, this creates this signal. And even if I don't have a working board, this is just kind of common sense. Like, this is a power signal. This is the input signal. I'm assuming that since this is going to another chip that's an output signal, I'm assuming something should be there. And I don't get anything here. So, since I have the input signal, I have the power rail going to this chip, but I don't have the output signal, I figured the chip was bad. So I replaced it. And that fixed that problem. Now my second problem, I got nothing on the screen. Obviously I don't have anything on the screen with that LVDS, and just in case you weren't paying attention earlier, here is how this board came in. Yeah, not the nicest looking LVDS now, is it? So, what did I do after that? After that, I decided to replace the LVDS, and now, after I replaced the LVDS, it looks something like this. A little better, I'd say a tiny bit of an upgrade. Yeah, just a little bit of an upgrade. Just a little bit of an upgrade. So, and now I have no backlight. Sad, sad me. So what do I do? Well, now I gotta start troubleshooting the backlight circuit. So one of the first things I like to do in troubleshooting the backlight circuit is measure the resistance to ground from backlight output. So let's fast forward here. So one of the things I like doing is measuring output of backlight to ground. So right over here, you'll see PPV OUT, SW, LCD backlight. These are the capacitors on it, and you can also measure it on the LVDS connector. And as you can see, I tied a couple of the pins of the LVDS connector together, because on this board, those pins from the LVDS connector, they're the same thing anyway. It also makes it easier if I put a nice amount of solder on there to do this measurement. Now the thing about measuring resistance to ground is that it takes a long time. If you're trying to measure the resistance of a resistor, you can do that. But measuring the resistance of across an entire circuit, you'll see that the multimeter just moves and it waits and it takes its sweet ass time. But if you use diode mode, it goes relatively quickly. So what I did here is I made a little measurement. So I put my multimeter's positive probe on ground and the black probe on the LCD backlight. And right now I get 0.456. 0.546 is what I get. So 0.546. I'm honestly expecting 0.519 because that's what I get usually on this board. And you'll see that different boards have slightly different values based on their backlight circuit. But after a while, you get to a point where you know exactly what the voltage drop should be to ground on that circuit. Right now I'm getting 0.546. That's actually scaring me. That's kind of making me wonder if I'm going to plug this in at the end of the video and you're not going to see a backlight. But the point is, that's one of the first things I do to test. And when I did that, and I got a number that was way off. I honestly don't remember the exact number, but it was a number that was way, way off. It was nothing like the number that I just showed you, and that told me that something here is missing. Now, if you get a number that's 0, if you get 0, that means that there is a dead short to ground. That means that somewhere in the board there is a dead short to ground. What that is showing you in diode mode is what the voltage drop is across the 2 points that you measured. So if there's a 0 voltage drop across the output of an amplifier or boost circuit in ground, that's no good. Most of the time if you get a 0, it means that there's a short direct, not even just a chip that went bad, I mean just metal on top of metal, and when that happens it's almost always the LCD connector. I can't tell you how many times I've had a dead short and I forgot to check the LCD connector until I tortured myself for like 10-15 minutes. It's humiliating. It's embarrassing, but I've done it, so which is why I'm telling you. Now if you have something like 0.6 or direct 0.4 or something like that, it usually means something in the circuit's not connected. And the most common thing that's not connected is the feedback trace. Now this is a really bad schematic to be showing this to you on. I don't know why the schematic is put out this way, I really don't. But the feedback trace over here is supposed to usually be from the output of backlight. So the way this works is this creates a backlight signal. Now the chip monitors it and pretty much puts out voltage based on what it's putting out. So it puts out the signal here. That then goes past this boost diode and you get the actual output of the backlight, and usually there's this feedback trace. Wouldn't it be great if I actually zoomed in so you can fucking see what I'm talking about? Now let's start that again. So right here you have the output of the backlight circuit, so SW. That is combining with the 12 volts that the machine is actually already creating. And then you have this diode. Then you have the output of backlight, and usually feedback is combined with the output. So the whole idea here is this is the output of the boost circuit, and then the chip monitors what it's putting out through feedback. And that's pretty much it. Now over here it says voltage 50 volts. So if something fucks up in this circuit, the first thing I'm going to check if I think something is burned is where there's the most voltage and directly on output. So most of the time this little trace is burned. Now as you can see on this board, feedback is actually just going up over here and then back to itself, which again I truly don't understand, because on every other schematic, let me show you another one, the feedback trace is tied to output. Let me show you, because on a different one. Yeah, so I'll actually show it to you on a retina board, because there's a retina board that uses the exact same backlight IC, almost the same backlight IC. So U9701. So the circuit is a little different. So yeah, feedback is going here, and then here goes to, yeah, after the diode, backlight output. So again, most of the circuits are like that. So I just figured something was corny and cheesy here and, fucked up with that other schematic. And now I tied the feedback trace, I tied the feedback pad of this chip to the LCD backlight output. And I determined the easiest place to do it here was right at the other side of D9701. So that's what I did, and I got a backlight. Now let me show you how I went about doing that. Again, most of the time when that blows, again, 50 volts. It's blowing with 50 volts, which means it is going to be just a ginormous clusterfuck. So what I did is I decided to, let me get you into the microscope camera now. I soldered this wire to the bottom of the chip. I soldered the chip onto the board, and then I soldered the other end of the wire to the end of the boost diode. And then I covered it with this green conformal coat. I also covered the components around it with the green conformal coat so that I wouldn't have to worry about this wire shorting. See this wire that's coming along right over here? See this wire that's coming right out like this? You see that pad? That's ground. That's ground. See that? That's amplifier output. That's up to 50 volts, and I am this fucking close to ground. So you can bet your damn ass that I conformal coded the fuck out of that before I put that wire there. So it's yeah, let's get another view. Because again, I don't know what I can't monitor this in real time. I can't monitor the actual video output in real time because my computer is, again, it's a nice machine, but this is not made for multimedia production. This is just a basic low-level ThinkPad. So I can't, and this camera up here, this microscope camera, all being really good, has a different magnification level from here. So I can't actually see everything in here up here. So yeah, I just gotta guess what it is you're seeing and move around. So that's the backlight chip. That's the wire. This is molybdenum, molybdenum, whatever the fuck it's called, wire. It's the shit that you use to fix Samsung phones. And it's going from underneath the chip. It's bending right over here and going up and around here. Now, that's the part that I fucked up over and over again. And again, you really, if you've been doing this as long as I have, you really should be at the point where that type of work is not difficult, is not frustrating to you. But unfortunately, to me, it still is. You know, you didn't get to see it because again, I forgot to keep the microscope camera on. Just take my word for it that I suck, and yeah, I do suck at that. So that did take me almost an hour to do. I am being honest. You know, again, even at my level, that did take me an hour. That's just embarrassing. But it is what it is. Let me show you what that wire looks like, by the way. Where is that garbage? Where is that horse crap? I remember when I bought this and I thought, I'm going to fix Samsung phones with this. I'm going to make money fixing. Yeah, I'm going to do glass-only repairs. And then I did one. And then I actually did one, and I'm like, no, I'm never doing this shit again. Fuck this shit. Fuck this crap. I hope that I truly hope that I'm never broke enough that is how I'm forced to make a living. Like just doing this and going like trying to rip little fucking shards of glass out of a phone. Just mindless, mind-numbing garbage of just even though to make $50. I truly hope that you know, again, God bless you if you're making money off of doing that. I don't want to do that. And this channel is about making money off of the things other people don't want to do. So again, truly, God bless you if you are making money. You are making good money doing shit that I don't want to do. But I don't want to do it. So this is the wire. Again, I've made $0 ever using this for its intended purpose. But I've made good money using this wire for this stuff. Now, the cool thing about this wire is it's almost impossible to break. So I can fuck with it a lot. And again, when you're bending the wire that's this thin over and over and moving it around, it's really easy for it to finally fray and just pop off. This stuff, again, it'll do that eventually, but it takes a lot of work for that, to do that. The other thing is it's not insulated. It's solid core, and it does conduct electricity on the outside, which means that you very well can, you know, if you short other things on there, or if it touches any of the probe points that it's going around, it touches any of the other components, you're fucked. Again, it's not insulated wire. So what I did, as you can see, is I covered it with this green conformal coat. I covered this shit, definitely, because that's fucking ground right there. And I covered all this other crap with it. And then after I actually put the wire there, I put more conformal coat over everything. I mean, I even conformal coated the fucking wire, because you just shouldn't have something that can go up to 50 volts just saying, hi, what's up? Yeah, I'm just hanging off the board. Just 50 volts attached to metal just hanging off the board. No, I'm not doing that. I don't want my friend's door to go on fire. So, that's that. And also, see how I bent it over here? There's a good reason for that. You see, I don't want the wire to just go up and like that. When I'm touching this, and I'm scared shitless to even touch this thing, so I'm not going to, even though I really wanted to prove a point. If this thing gets touched, I don't want it to bend at the solder joint under the chip. I don't want any of the bending to happen over there, because then I have to take that fucking chip off and solder the wire to it and put it back, and that's a pain in the ass. So what I did is I bent it over there so that if I touch it, and again, I really want to touch it to show you, but I really don't want to redo this if I break it. If I touch it, it's going to bend at the bended point. I don't want it to bend near here. See, that's why this bend is over here. I don't want this wire to bend or to move, and for it to just touch ground and for me to blow up the board. So now if I move it, it's going to be a little hard. It's going to move where this coil is. It's going to put the pressure around where the little coiled part is. So that's why I did that. Now, how do I solder this thing onto the chip? That's a pain in the ass. So what I do is, before I put the QFN package down, excuse me, I'm waiting to go to dinner. I just want to see if this person is coming. See? Okay, I guess you're not. Such is life. So the way I solder that underneath the chip is I use a combination of leaded and lead-free solder. Now, lead-free solder has a higher melting temperature. Lead, it's like 217, 235 Celsius. Leaded solder has a temperature around 180 Celsius. Now, the idea here is that I can solder the chip onto the board with the leaded solder. And while I'm doing that, I can use an amount of heat that's not going to melt the lead-free solder. So the whole idea is after I put this wire on and then I go to solder the chip on, I don't want that fucking wire to fall off as I'm putting this down there. That would suck. So what I do is I use the lead-free solder to solder the wire to that pad under the chip, and then I solder the chip onto the board. And that makes the whole process a lot easier. I had to solder to the chip directly because there's no pad there anymore, and I'll explain on that a little in a minute. So, oh, by the way, on the whole topic of leaded versus lead-free solder, you're going to hear a lot of crap on how lead-free solder is better because it has a higher melting temperature. Let me show you just what a crock of pile of dog shit that is. So watch this. Watch this is why lead-free solder is shit. Here, let me show you something. So see this? This is the original ISL chip using lead-free solder. This is the solder from the factory. So I'm going to go at 30x here, and I'm going to fuck with it a little, and I'm going to show you why I think lead-free solder is a bunch of shit. So watch this. This is a multimeter probe here. Watch what happens if I touch this with the multimeter probe. Watch, I'm going to touch it. Not even that hard. It's, you know, ding. See that? Look, I just ate away at a quarter of that fucking joint. I ate away at a quarter of it. It just went boom. It's gone. If I touch it again, watch. Well, let's see what happens again. I'm going to touch it from the other side. Look at that. This stuff is crap. Now let's try leaded solder. Let's try my leaded Kester stuff. Let's go to the LVDS connector. We're going to go to the LVDS connector that I replaced. By the LVDS connector, there's these two pins for backlight that I soldered together. And at the LVDS connector, let's try touching it. So I'm going to touch it with the probe. Okay, didn't leave a dent. Let me try pushing. Barely leaves a dent. Let me try pushing really hard. Finally leaves something that's about the same size or slightly smaller than what I left on the ISL. So yeah, that's the thing with lead-free solder. I mean, you could tell me all you want about the melting temperature and how it has a higher melting temperature, but this stuff, it fucking sucks. It really... Alright, so apparently one of these little video capture devices that I have, this thing, one of these works really well, and one of them works like complete dog shit. So for 2 minutes there was no video on the microscope. Anyway, I'm going to have to get a new one. So anyway, let me go back to what I was talking about. I was talking about leaded solder versus lead-free solder for a second, and I was talking about the benefits of using leaded solder. So I was just going to do a little presentation here. Hopefully this doesn't die again, because that would suck. You know, you kind of get what you pay for. Seriously, I was wondering, why does, Osprey have a card that's $1,800 that does the same thing that these little USB dongles do for $300? Because the quality control on this stuff really sucks. And again, you're going to find with a lot of products that you find a product that does exactly the same thing that another product does to the same level of quality, and you're going to wonder what the price difference is all about. And then you buy it, and like you buy 10 of them, and only 3 of them work. It's when you spend money on something, it's not just about that. It's about the consistency and the quality. But again, good luck finding a USB 3 video for Linux HDMI to USB 3 dongle. That's good quality. So okay, so here is the ISL 6259. This uses lead-free solder. Now I'm going to do a little demonstration here. See this right over here, where I'm touching it with my microscope probe? Watch this when I push it. Look at that. This solder is horse crap. This is lead-free, and you're going to hear, again, people are going to go, lead-free solder is better because it has a higher melting temperature, and the computers operate with a really high temperature, so the lead-free solder is actually better, and it's more reliable, and that is just a bunch of fucking horse crap. And let me show you the leaded solder over here. So let's go up to the leaded solder. You better stay on microscope camera. Alright, so leaded solder right here. This is, now watch what happens when I push it. See, I'm pushing, nothing. I touch it, nothing, nothing. See this? Look, I'm putting it right there. I'm not getting anything. Watch, I push really hard. Nothing. I'm going to push harder. Let me refocus it because you kind of lost the view. I'm going to push really hard now. See, now you finally chip away at it, but you gotta push really fucking hard. The other one, I put the probe and I go dink, dink. That's all it takes, and it just wipes the solder right off. But anyway, the point is here. I used lead-free solder to solder the wire to the bottom of the pad on the chip. And then I solder the chip to the board using leaded solder. Now again, the wire is going to get moved around quite a bit. This wire is going to get moved. How, especially, and it may even move around a little bit and come off a tiny bit because you are heating it to 180, 190 Celsius to put this chip back. But it's not going to be as bad as if you had soldered it with leaded solder, because you solder it with leaded solder and it's just going to come right off. It's going to fly right off immediately, and that is no good. That is crap. So if you use lead-free solder to solder the wire to the bottom of the chip and then leaded solder to solder the chip to the board, you stand a fair chance of that wire actually being somewhere in the vicinity of the solder pad that you intended it to be at. And that's a good thing. So that's pretty much that, and I turned it on and I got a backlight. But looking at that, I truly do not expect you to believe me. This person is going to keep calling even though I'm closed, by the way. That's just kind of what people do. It's like, it's not enough that you call and nobody answers and it's 20, 30 minutes after the closing hours. Freaking phone. Freaking phone. Alright, so let's go back to where I was before I got interrupted. Let's see. Yes, it was to plug this in and see that it works. Yes. I'm sure it will work just fine, even though the measurement I got on my backlight output was completely different than it was when I tested it 1 day ago. I'm sure it will be fine. See, confidence is a big thing. For some reason, if you're confident that it works when you plug it in. Negative people suck at repair. They really do. Because negative people, the shit never works. It never, ever works. You gotta look at the board like, fuck you. You are gonna turn on. You are gonna have a light. You ain't gonna give me any of that running slow shit. You're not gonna give me any of that GPU defect bullshit. No, you're gonna work when I turn you on. Now this is a Core 2 Duo board, and I don't feel like finding a heatsink for this video. To be honest with you, today I just really want to go home. So I'm not spending that much time on it. So I'm gonna plug this in without the heatsink, because it is a tradition here to show you that the work that was done actually works. And I'm gonna keep it on for a very short amount of time, because being a Core 2 Duo board, the CPU will heat up insanely from the second that I turn it on. And I don't want to blow it up, particularly because it belongs to a friend. And he'll be happy that I didn't blow it up. I'm sure that he'd much prefer that I don't destroy his board before I send it back to him. But if you are actually going to run the Apple service diagnostic and stuff like that, or run firmware or any kind of test on these boards after you're done with them, attach the heatsink and also attach the fan by one screw. It's don't run. I've actually seen people running those tests without a heatsink, and like you're just nuts. There are times on rare occasion where I don't have a heatsink for a specific board, so what I do is actually stand there with the air compressor and just keep it blown on there. And that does it. Okay, cool. So my tweezers are so filled with conformal coat that I can't even short this to make it turn on without like 5 tries. I also don't have my LVDS plugged in all the way, so yeah. Should definitely plug that all the way before the screen kicks in. That would be the smart thing to do. And also, so I know when the thing finally does turn on, I always have a speaker somewhere here. Come on, where are you? Where are my desk is truly shameful. I gotta make this look neater. The thing is, before I do a video, I actually clean this up a good amount. I mean, if you saw what this looked like on a regular basis, you probably wouldn't send anything. You wouldn't send anything here. Oh man. Alright, so I got a speaker so I'll know when it chimes. Come on. Hallelujah. Backlight. And I don't have any of those little black fucking bars, shadow crap things going on the bottom of the screen. So I'm good. I'm happy. My board's not happy because it's boiling, but that's why I turn it off. Hopefully you learned something. Hopefully this has encouraged you to try and learn something if you have not learned something from the video. And that's it for today.